Welcome everyone to the fourth talk of the SwissCat seminar. Our speaker for today is Benedek Dombos, who will be talking about crystals of type A. So go ahead.
Yeah, thank you so much. So, let's mute that one. Thank you. So thank you. The title of this talk is Crystals of Type A. Admittedly, a bit flashy, but I just wanted to show you some pretty pictures of crystals. But before that, let me start with a nice little problem about the Pascal triangle. So the question is, what is the square sum of the entries along a row of the triangle? For example, for n equals 2 in the second row, the square sum of the entries is 1 plus 4 plus 1, which is 6. In the third row, the sum of squares is 1 plus 9 plus 9 plus 1, which is 20. And in the fourth row, the square sum is 1 plus 16 plus 36 plus 16 plus 1, which is hopefully 70. So it looks like the square sum of the entries in the nth row is just 2n choose n, which is the entry that we can obtain by reflecting the tip of the triangle on the nth row, for example, like this. Well, to show this, one can interpret each entry of the triangle as the number of shortest paths from the tip of the triangle to that entry. For example, for 6 choose 2 equals 20, which is a number of paths of length 6 from 0 choose 0 to 3 choose 2. Each of these paths crosses the middle row at exactly 1 point, so we could just count them separately. For example, the number of shortest paths from 0 choose 0 to 3 choose 2 is just 3, because that's the value of 3 choose 2. And by symmetry of this construction, this is also the number of shortest paths from 3 choose 2 to 6 choose 3. So altogether, the number of shortest paths from 0 choose 0 to 6 choose 3 is just 3 choose 2 squared. And looking at this disjoint union decomposition of our paths along the middle row, we obtain the formula for the square sum. But alternatively, we can also show this formula by factoring 1 plus x to the 2n as 1 plus x to the n times 1 plus x to the n, and picking out the coefficient of x to the n on both sides. So on the left-hand side, it will be 2n choose n by the binomial theorem. And on the right-hand side, we could choose x k many times from the first factor and n minus k many times from the second factor. So altogether, coefficient of x to the n will be n choose 0 times n choose n plus n choose 1 times n choose n minus 1, and so on. And by symmetry of the Pascal triangle, this is just equal to the square sum, so like n choose 0 squared plus n choose 1 squared up to n choose n squared. Well, there's another set of paths along the Pascal triangle whose cardinality happens to be 2n choose n. And well, so the starting point will again be the tip of the triangle. The length of each path is again going to be 2n, but the endpoint is no longer fixed, and instead we impose the additional condition that a path can't venture into the left side of the triangle. So in this example, we have length equals 4, and we have 4 choose 2 equals 6 many paths under these conditions. So these paths can be conveniently represented by words in 2 letters 1 and 2, such that when read from right to left, the number of 1s is always at least as big as the number of 2s. So to obtain that, we have to read our paths from like upwards like this, and for each left move we write a 1, and for each right move we write a 2. So here we have all 6. So yeah, words like that, satisfying that condition, are called Yamanouchi words, and we have all 6 Yamanouchi words in 2 letters of length 4 corresponding to our previous paths. Well, we could count them recursively for an arbitrary length, I guess, but here for the purpose of this talk, I would like to introduce, or I would like to create a very concrete bijection between a set of Yamanouchi words and a set of our earlier paths. So the earlier paths can also be represented by words of ones and twos, such that the number of twos is equal to the number of ones. And so we have 6 of those again. We would like to construct a bijection. Well, if you've seen those things before, you might notice that the intersection of these two sets consists of dig paths. And in many contexts, it is expedient to represent dig paths by well-bracketed expressions. So to each letter 2, we'll associate a left bracket, and to each letter 1, we'll associate a right bracket. And then we get these nice well-bracketed pairs of brackets. But we might as well do the same thing for the Yamanouchi words that are not dig. And but here we will get some unbracketed right brackets. So we'll denote the bracketed brackets by red and the unbracketed right brackets by blue. And well, the dig paths already lie in our target set, so we don't need to change them. But we would like to alter the other Yamanouchi words in a way that doesn't change the position of the red brackets. And there's only one way to do that. We'll have to change the rightmost unbracketed right bracket, so rightmost blue bracket, into a left bracket. So rightmost unbracketed 1 into a 2. For example, this one here will turn into a 2. This one here will again turn into a 2. This turns into a 2, and this turns into, no, this one turns into a 2, sorry. So this way we obtained almost all our target sets, but we still have some blue brackets, so we might as well carry on and see what happens. So eventually we just obtain some strings of words starting from Yamanouchi words. And our target set will lie in the middle of these strings. And also, it's an important observation that all words, all 16 equals 2 to the 4 words in 2 letters of length 4 would be contained in this picture, because the arrows are invertible. So they're invertible by turning the leftmost unbracketed 2 into a 1. And also, Yamanouchi words are exactly the ones without any orange brackets, because if we have an unbracketed 2, then by definition, we can't have an unbracketed 1 to the right side of it. So if we cut this word here, then the number of 2s will be larger than the number of 1s, which would violate the condition of the Yamanouchi word. Okay, so if you've seen Lie algebras before, then this picture might be reminiscent of representations of SL2, in particular SL2 strings, which are finite dimensional irreducible representations of SL2. But and this is indeed the whole point of my preamble. So I feel like I should quickly rifle through that story as well. Okay, so Lie algebra SL2C is a vector space of traceless 2x2 matrices. So trace equals 0. Endowed with a commutator bracket that is defined by x bracket y equals x times y minus y times x. And as a vector space, it's 3-dimensional. There's a distinguished basis that's given by these matrices E, H, and F, where E is upper triangular, H is diagonal traceless, and F is lower triangular. This basis is distinguished because the expression of the commutator bracket has a simple form on this basis. So E bracket F is just H bracket F is minus 2F, and H bracket E is 2E. And for our purposes, the main point of this is that we'll be looking at representations of SL2. So a representation of SL2C is just a linear map from SL2C to a vector space of endomorphisms of a fixed vector space V. And if we also fix a basis, and it just means that to each element of SL2C, we assign an n by n matrix, and it could be zero matrix. It's not necessarily invertible, such that this linear map respects the brackets. And irreducible representations are the ones that have no non-trivial invariant subspaces, and these will be exactly the SL2 strings from the previous picture. So just let's see a few examples to see what these strings are. So SL2C is acting on a two-dimensional vector space C2 with natural basis E1 and E2. And the H eigenspaces of this action, which would be the weight spaces in a much more general context, will be the C-span of E1 and the C-span of E2. And the action of F, just by matrix multiplication, will take C-span of E1 to the C-span of E2. So this will give us some two-string. SL2C also acts on a three-dimensional vector space quite naturally, namely itself by the brackets. And this is the adjoint representation. And by looking at these formulas here, we can see that the H eigenspaces are going to be the C-span of E, C-span of H, and the C-span of F. Well, H bracket H is zero either by the definition of the commutator or by anti-symmetry in characteristic not equal to 2 if you just want to look at these expressions. But okay, so the action of F by the same formulas also takes the C-span of E to the C-span of H, and then the C-span of H to the C-span of F, and then the C-span of F to 0. So it will give us a free string. And in general, all irreducible representations of SL2C will be of this form. They can be constructed explicitly by looking at the vector space of homogeneous polynomials in degree D in two variables, x and y, and looking at the monomial basis, so y to the d, y to the d minus 1x, and so on, up to x to the d, and letting F act on this vector space by the operator y times partial x. And then the action of F will take the C-span of x to the d to the C-span of y to the d minus 1, and so on, and it will create this long string of length d plus 1. And okay, these representations are irreducible clearly, because if we also take into account the action of E, all these things will be wiggled around, so it will be irreducible. There are no invariant subspaces. Okay, so in light of all this, the previous picture will be a combinatorial model for the action of SL2C on the vector space full tensor product of C2. So SL2C acts on C2 by matrix multiplication, and this action extends to the tensor product by the usual thing on Lie algebras, the derivative of the diagonal action. But if you haven't seen this, it's not so important. And then, so this picture is referred to as a crystal of all words in 2 letters of length 4. And admittedly, the connected components, which are the irreducible representations, are a bit dull because they're just strings. But the multiplicities are still quite interesting. So let's look at the multiplicity of the trivial representation. The trivial representation is just a one-dimensional representation of assigning any element to any element the zero endomorphism. So let's look at the multiplicity of this. Well, by the path model, we can see that the singletons are exactly the dig paths. So this is just tantamount to counting a number of dig paths. So dig paths are just paths, lattice paths from 0, 0 to n, of length 2n, such that they stay above the diagonal. So for a 2x2 grid, we have 2 dig paths, like on the previous picture. For a 3x3 grid, we have 5 of them, and for a 4x4 grid, we have 14 of them. And in general, they can be counted in a pretty nice way. by looking at all paths first. That would be 2n, choose n, and then dismissing all the bad ones. So the bad paths are exactly the ones that cross the diagonal at some point. And well, if you cross the diagonal, you're bound to at least touch this pink line below the diagonal. So the statement is that all the bad paths, from the set of bad paths, there's an explicit bijection to a set of all shortest lattice paths from 0 to n plus 1 and minus 1. And this bijection is given quite explicitly for these paths by reflecting the part of the path after touching this pink line to the pink line. So here, for example, yeah. Okay, so this is one example where the path model can be quite useful to say something about representation theory, in particular multiplicities. But you get more interesting connected components if you increase the number of possible letters. So here we have all 27 equals 3 to the 3 words in 3 letters of length 3, and the connected components will be indexed by Yamanouchi words again. But what are the arrows? So the blue arrows will be defined as before on the strings of 1s and 2s by just forgetting about the letters 3. And this will correspond to, the whole picture will correspond to the action of SL3C on the threefold tensor product of C3. That's quite a tongue twister, which is denoted by B33. And the blue arrows will correspond to the action of this Chevalier generator, the first Chevalier generator in SL3. And the red arrows are defined in much the same way, only the rows of 1 and 2 are replaced by the letters 2 and 3. And we forget about the 1s. And this will correspond to the action of the second Chevalier generator. And then crystals of type A can be defined as some union of connected components in some crystal of words like B and K, with possibly possibly higher multiplicity, so possibly more components on top of each other. And they would correspond to some representation of SLKC. So one particularly nice aspect of crystals of type A, before that, I should probably mention that it's called crystals of type A because it corresponds to a type A Lie algebra, but this notion can be generalized widely to all Kac-Moody algebras, which I will not define here, so I will stick to type A. So it's a nice feature of crystals of type A, and actually crystals in general, that we have a simple description for tensor products. So let's take 2 irreducible representations. Here, SL3C is acting on C3 by multiplication. This is just a crystal of all words in 3 letters of length 1. And we tensor this with a connected component of V tensor V. This connected component in particular will have letters that are increasing or non-decreasing this way. Okay, so we know that this guy is in V, this guy is in V tensor V, so the tensor product should be in the threefold tensor of V, which is modeled by this crystal B33. So 3 letters and length 3. What we don't know, what we have to identify is up to isomorphism, what are the connected components. And there's for words, there's a nice way of identifying this just by concatenating the words. So that's a theorem that the corresponding vertices will be just the concatenations of the vertices in the 2 words of the 2 crystals. And the arrows will be all the arrows induced by the big crystal B33. But this description is quite nice, but it also requires us to refer to the particular embedding. And it would be nice to have an intrinsic description just based on the arrows. And to this end, we know that the definition of the arrows in the crystal of all words is completely independent. So we can just focus on the strings and try to find an intrinsic description for the tensor product of strings. The tensor product of these two, by concatenation, we know that it will be a union of a 4-string and a 2-string, but we would like to establish that just based on the arrows. And thankfully, Kashiwara has such an intrinsic description. So we forget about the vertex labels of words, and instead we're just going to write letters A, B, and C, D, E. And quite gratuitously, we'll just introduce 2 functions, phi and epsilon. But before that, I would like to note that in the tensor product, the vertex set is just going to be the Cartesian product of the 2 original vertex sets. So basically, we just have to determine on which factor a given arrow is acting on. And if we know that, we can just refer back to our previous crystals and see what happens there. So phi of a vertex will be the number of times we can go forward from that vertex along the arrows. And epsilon will be the number of times we can go backwards along the arrows. So phi of A will be 1, phi of C will be 2, and phi of E will also be 2. And then Kashiwara showed that that if we jot down phi of the first factor here and phi of the second factor here, and by an epsilon of the second factor here, and by this we can establish which factor we're acting on. So if phi of the first factor is larger than epsilon of the second factor, and we're acting on the first factor, otherwise we're acting on the second factor. So on this picture, in particular, we only act on the first factor here, and we act on the second factor for all the other tensors. Okay, so and now we know what we're acting on, we can go back to the original strings. So A will go to B because of this one. C will go to D, D will go to E, and E will go to 0. And here D will go to E and E will go to 0. Okay, so this is like a nice intrinsic description of the tensor products. And this actually holds for all the crystals that we're not going to define here, not only in type A, but even in type A, it's quite useful because the vertex labels might naturally be different from the labels of words. And we might want to stick to those vertex labels and don't convert it to the crystal of words. And in the remainder of this talk, I would like to show you an example. I would like to construct a crystal where a crystal of type A, which is indexed by some other objects, not words. And setting the stage, I would like to say a few words that would be quite pertinent for this seminar in general because of the Zoom password, S3 order. So a representation of Sn is just a group homomorphism from Sn to the automorphism group of a fixed vector space. And for example, S3 acts on a 3-dimensional vector space with fixed bases x, y, z. And by definition, basically permuting these basis elements. So we have the 6 representing matrices here. And for example, the representing matrix of the 3 cycle 1, 2, 3 is going to be this one. And indeed, if we multiply by matrix multiplication, this matrix sends x to y and y to z and z to x as it should, because it's a 3 cycle. But this representation is not irreducible, i.e. there's an invariant subspace, non-trivial. The one spanned by the vector x plus y plus z. And it's invariant because for any G in S3, the action is linear, so we can split the bracket. And also, a set g of x, comma, g of y, g of z is the same thing as the set x, y, z, because g is a permutation. So in particular, this sum is equal to this sum. Sorry. Yeah, sorry. We have an invariant, non-trivial invariant subspace, and that's a general fact for finite groups, that we can always construct an invariant complement to this subspace by a suitable invariant inner product. And if, in particular, any representation decomposes as a direct sum of irreducibles for finite groups. And if we pick a basis in these respective components, for example, here we have x plus y plus z, and y minus x, and z minus x, then all the representing matrices will be block matrices of the same shape. So here it looks like this. So that's one fact that we'll need from representation theory. And the other object that we'll need is characters. So a character of a representation is a map attached to the representation from Sn to C, which is given for each element by taking the trace of the representing matrix. For example, for the defining representation that we saw before, this one here, the trace is just a number of fixed points. So for the neutral element, we have trace equals 3. For the transpositions, the trace is equal to 1. And for the free cycles, the trace is equal to 0. And it's, again, a general fact about finite groups. Oh, sorry, before that, I should mention this thing here, that the trace is the sum of eigenvalues. So it's invariant under conjugation. And so the character is constant on conjugacy classes, i.e. it's a class function, as we saw it here. And in general, for finite groups, irreducible characters determine irreducible representations and form an orthonormal basis of class functions. So, for example, for S3, the conjugacy classes are here. They're classified by cycle type. So for the neutral, we have the neutral element, we have transpositions, and we have 3 cycles. And if we write the cycle types in a way that also displays 1 cycles, and we see that there's a bijection from conjugacy classes to partitions of 3, so 1 plus 1 plus 1, 2 plus 1, and 3. And this holds in general for any symmetry group Sn. So irreducible representations of the symmetry group correspond to Sn correspond to partitions of n. And this index set of partitions is particularly nice because lots and lots of things in representation theory can be described purely based on the combinatorics of the indexing partitions. So the archetypical example of that would be the dimension of an irreducible representation. So let's take a partition, let's say 3 plus 2 equals 5, and we'll represent it by the Young diagram, which is a left-aligned diagram here that will have three squares in the first row and 2 squares in the second row. And we look at fillings of this diagram with numbers 1, 2, 3, 4, 5, such that the numbers are increasing along the rows and also along the columns. And these fillings are called standard Young tableau. And so the dimension can be described as the number of standard Young tableau of this shape. So for example, here we have dimension 5 because we have 5 standard Young tableau. And here it's easy to write it down explicitly, but there's also an effect, quite a nice formula for counting these things. So for each box of the diagram, we'll assign a number, which counts the number of boxes that are to the right and below this box, including itself. So here we have 1, and 1, and 3, and 2, and 4. And the formula says that this number is equal to the number of factorial of the number of boxes over the product of these numbers, which are called Hooke numbers. But a striking fact about these numbers is that if we take all partitions of 5, say, so 5, 4 plus 1, 3 plus 2, and 3 plus 1 plus 1, and so on, all 7 of them. And let's look at the numbers of standard Young tableau for each given shape. So we have 1, 4, 5, 6, 5, 4, and 1. And take the square sum of these numbers. So 1 plus 16 plus 25 plus 36 plus 25 plus 16 plus 1. We get 120, which is very conspicuously equal to 5 factorial. And this is in fact this is a general fact. So you always get n factorial if you take these square sums for any symmetric group. And there is some representation theory behind this. So if you take the n factorial dimensional vector space CSN, whose basis elements are indexed by permutations, and act on it by Sn by left multiplication of the indices. And this is very far from being irreducible. In fact, it contains all irreducible representations of a symmetric group. And the dimension of each irreducible component is going to be equal to its multiplicity. That's where this square sum comes from. And this is, in fact, this is true for, think about dimensions and multiplicity is true for general groups acting on the group algebra, finite groups. But finite groups in general don't have such a nice combinatorial expression for the dimension of irreducible representations. But for the purpose of this talk, I would like to prove this fact combinatorially, not via representation theory. So we would like to construct an explicit bijection from a symmetric group, Sn, regarded as a set, to pairs of standard Young tableau of the same shape over all partitions of. So let's take a permutation pi in 2-line notation, which means that 1 goes to 4, and 2 goes to 2, and 3 goes to 3, 4 goes to 6, and so on. And the first line just contains consecutive numbers. So the red line is the essential line. And we would like to construct a standard Young tableau from a red line of numbers. And the strategy will be to read this line from left to right. And each consecutive number will be inserted into the first column. Well, this is, of course, easily feasible if everything else is smaller than the new number. And the new number can just slot right at the end of the first row. But if there's a number in the row that's larger than the new number, and this new number will replace this old number and bump it down to the second row, and then we'll do the same procedure with the old number in the second row. That's a lot of words, so let me just show you this example here. So we'll start from the empty tableau. We'll insert a first number 4, and then we'll insert 2, but 2 is smaller than 4, so it bumps 4 down into the second row. 3 is larger than 2, so it slots in behind 2 in the first row. 6 is larger than 3, so it slots in behind 3 in the first row. 5 is smaller than 6, so 5 bumps 6 down into the second row, and 6 is larger than 4, so it slots in behind 4 in the first row. And 1 is smaller than 2, so it bumps 2 down into the second row, and 2 is smaller than 4, so it bumps 4 down into the third row. And 7 is larger than 5, so it just slots in behind 5 in the first row. So that's the algorithm for producing the so-called insertion tableau, which recalls sort of the second line. But this is far from being able to determine the permutation, even for S3. For example, these two permutations would yield the same insertion tableau, and also these two permutations yield the same insertion tableau. But what's different in these two procedures is the actual order of creating this insertion tableau. So if we can keep track of the shape of growing this tableau, then we can determine the permutation. And this is what the first row is used for. So as the shape grows, we'll just insert consecutive numbers. So for here we have 1, and then 2. How does it grow? 3, 4, 5, 6, and 7. And then from this, we can actually reconstruct our permutation. And the fact that it's actually a bijection is, of course, an important theorem. But we didn't really use anything about permutations in this construction. So instead, we can just start with any word that we had in the first part of the talk. Just start from k to the n of words in k letters of length n. And well, the second tableau will be the same. It's just recording the growth of the diagram. But for the first tableau, we might have some repeated letters, and all the repeating letters will be in the same row, and we'll produce a tableau where the numbers in each row will be non-decreasing, and the numbers in each column will be strictly increasing. These tableaux are called semi-standard Young tableau of shape lambda, and possible letters 1 to k are denoted by k. And again, there's a bit of representation theory behind this. So, well, let's take a vector space V equals c to the k, and then GL kc is acting on this by matrix multiplication. This action extends diagonally to the n-fold tensor product of V, but also Sn acts on the n-fold tensor product by swapping the tensor factors. And these actions commute, so this induces, or this endows a vector space, n-fold tensor product of V, with a GLKC Sn bimodule structure. And Schurwald duality, which is one of the cornerstones of, I guess, combinatorial representation theory. Schurwald duality states that this, as a bimodule, this decomposes as a direct sum of tensor products, where the L's are irreducible representations of GLKC, so GLKC modules, and the Sn are irreducible representations of Sn as before. Well, if we take dimensions on both sides, and we see that the dimension of this guy is k to the n, the dimension of this guy, we saw the number of standard Young tableau of shape lambda. So the dimension of this guy should be a number of semi-standard Young tableau of shape lambda and lattice from 1 to k. And if we look at the index set, well, for this to be non-zero, we'll need partitions of n. And for this to be non-zero, we want the dimension also to be non-zero. Because it's counted by standard Young tableau, and standard Young tableau are increasing along the rows, a number of columns is supposed to be smaller or equal than k, which is a possible number of letters. Okay, so now we have a bijection from words to like pairs of tableau, and we had a crystal structure on words. So now we can introduce a crystal structure and something that is related to partitions, which is a very good thing because partitions index irreducible representations. So what we'll do is take the image of, send each word to its insertion tableau, which was the first tableau here, so this one, through the RSK, and take the arrows induced by the arrows that we had on the crystal of words. So this way we create a crystal of tableau. But we can't necessarily go back because for it to be a bijection, we need to make a choice. We need to find a standard Young tableau Q of this shape. And this will correspond to some reading of the tableau. In this case, it's this sort of reading. So, for example, the preimage of this tableau will be just 3, 1, and 3. Okay, and because we can't canonically go back, it's very nice to have an intrinsic way of computing tensor products. But what kind of things can be obtained by being able to compute tensor products of these guys intrinsically? Well, for that, let's try to forget about the vertices first. And yeah, so if we forget about the vertices, then the two graphs are ostensibly isomorphic by flipping the arrows or by sending red arrows to blue arrows. And also the point of this slide is really to say, like, thanks, Alex, for the beautiful code producing beautiful pictures. But yeah, after that, because we see that if we forget about the vertices, this no longer determines a representation, because these are different partitions. They correspond to different representations. So we'll have to add something. So we'll assign to each semi-standard Young tableau a weight, which would be a monomial. So to each tableau, we assign a monomial whose variables are indexed by the multiset of entries. For example, this tableau will receive the monomial x1 squared times x3 because there are two ones and one 3. And if we take the square sum of all these monomials, and we get something called a Schur polynomial, which turns out to be the character of the GLK-C representation corresponding to this partition. And there are quite a few striking properties of Schur polynomials. First of all, they are symmetric. And to see that they are symmetric is not immediate from the definition. But, well, we know that simple transpositions, so swaps like I and I plus 1, generate the symmetric group. So for Schur functions to show that they are symmetric, so they are invariant under any permutation of the variables, it suffices to show that they are invariant under the permutation of the variables like I and I plus 1. So we need to find an involution on the set of semi-standard Young tableau of a given shape and content, such that that swaps the number of i's and I plus 1s for each I. Well, let's try it for like 2 and 3. So if we just do that on the face of it, and we don't necessarily produce semi-standard Young tableau, so that's what we have to be careful about. So we're going to fix the pairs of 2s and 3s when 2 and 3 are in the same column, which happens if and only if 2 is right above 3. And for the rest of them, they will be free, and we'll swap the number of 2s and 3s in each, swap the number of 3 2s and 3s in each row. So for example, in the first row, these guys are going to be free. There will be 6 2s and 1 3. So, and here there will be 1 2 and 6 3s. So we'll do that. That will be an involution, and it's well defined for semi-standard Young tableau, and it shows that Schur functions are symmetric. Not only are they symmetric, but they also form a basis of symmetric polynomials. Yeah, Schur polynomials, sorry. I keep saying Schur functions because I'm being very, very cavalier about the number of variables. But yeah, so they form a basis of symmetric polynomials, which I can show, which I can prove by a nice convincing example. So there's a family of symmetric polynomials that are very ostensibly like form a basis. So to each monomial, each partition, we can associate the sum of all monomials of that shape. For example, for 2 1, you can associate x1 squared times x2 plus x1 times x2 squared plus x1 times x3 squared, and so on. And monomial symmetric polynomials will be a basis of symmetric polynomials quite clearly. And if we expand Schur polynomials in terms of monomial symmetric polynomials, then we get and the transformation matrix is going to be unipotent. So if monomial polynomials were a basis, then Schur polynomials also have to be a basis. So what we can do now is multiply two Schur polynomials that will also be a symmetric polynomial and expand it in terms of Schur polynomials again. And the coefficients that we get are called the Littlewood-Richardson coefficients, which are quite a celebrated notion in combinatorial representation theory. And again, the theme would be, according to the theme, the question is to find a purely combinatorial formula for these numbers only based on the indexing partitions. And representation theoretically, this would mean that we're looking at the tensor product of two irreducible representations, and we would like to expand it in terms of irreducibles and find a multiplicity. And this is one problem that can be solved via the crystal of Tableau. And here the intrinsic description of the tensor product would be quite important. But yeah, I guess I would like to probably stop here because the proof is quite cumbersome. So thank you so much for listening to my talk, and just let it cook, I guess.
Okay, are there any questions for Ben? I suppose I'll ask a question. What are the big open questions in crystals at the moment?
So, okay, so for crystals of type A, I'm pretty new to the topic. So I don't know, I can give you like one example that's a big question in combinatorial representation theory, and people suspect that it's related to crystals. Mm-hmm. So if you take here, for the Littlewood-Richardson coefficients, you actually have a combinatorial formula which can be proved via looking at crystals. But if you take the tensor product of two irreducible representations of the symmetric group, let's say S lambda tensor Sn mu, and you again want to expand it in terms of irreducibles, so some G lambda mu nu S mu lambda, something like this. These are called the Kronecker coefficients. And I mean, representation theoretically, you have some formulae, but there's no formula that only depends on the underlying partitions. And that's a long-standing open problem in this area. And people suspect that one of the big stumbling blocks is that for the symmetric group Sm, there's no crystal structure. Mm-hmm. And yeah, I guess if you can somehow circumvent that by understanding this proof well enough, that's a big leap. But mainly in my project, I'm dealing with affine crystals and relationship between finite crystals and affine crystals. You can basically ask anything, and it's unknown, like anything in this topic for finite crystals, like RSK or Littlewood-Richardson, mm-hmm. These sort of problems. Yeah, so I guess that's some sort of, in a nutshell, it's some sort of answer.
Yeah, does it? And you mentioned about like those coefficients. Like, does this have any connections with anything else? With, I mean, like the type A coxet groups or anything like that? Or?
I mean, yeah, symmetric group. But in terms of other coxeter groups, I don't know, because I don't know any combinatorial models for even like the dimension for other coxeter groups. So it would be a difficult question. Yeah. But yeah, I don't know.
Well, should probably see if anyone else has any questions. Does anyone else have any questions? Okay, if there are no questions, let's thank Ben one more time.